In today's lecture, we'll talk about a three-phase full-wave rectifier, controlled rectifier with R load, with a resistive load, and with a small firing angle. But before going to this one, let's say we have a sine wave, a three-phase sine wave, similar to what we see here. We have phase A and phase B, phase C. Let's define the angle first. Okay, because this will make our life easier when we go to converting this phase voltage to the line voltage, and then see where this firing angle works. The time from here to this is a full period, and if we divide this by 3, you'll find that the duration from here to here is 120 degrees, and here also 120 degrees, and here it's 120 degrees. So when we say this is 120 degrees, this is 60 degrees, right? From here to here is 60 degrees. And if the firing angle is between 0 and 60 degrees, if the firing angle starts from here, from this point to this point, this means the next waveform or the current waveform will not hit the 0 line before the next firing angle takeover. At this point, you'll find phase AB can hit the 0 line, and this will be 60 degrees. But make sure that here, before going to this one, if this is 60 degrees, the phase shift between the phase voltage and the line voltage is how much? Is 30 degrees, right? So this is 30 degrees. This is the phase shift. And also make sure for the three-phase full wave rectifier, the output voltage is the difference. It's VA minus VB, which means the line voltage. So this must be taken into account. So what happens here? For example, if VA is greater than VB and VC, you'll find that VA voltage will go this way, but without firing angle, nothing will happen. So the voltage, the current will be waiting here until the firing signal is sent to the gate, and then the thyristor will allow the current to flow. The same thing here will happen. Here you will find that we are looking for the smallest voltage. So for example, from here to here, you'll find that the output voltage is what? Is VAB, right? Why? Because the greater is VA, the smallest is VB. Now at this point, you'll find that same thing. The greater is VA, okay, but the smallest is VC. So we expect that the output is VAC, but this VAC will not take over until VA and VC, okay, thyristor 1 and thyristor 6 receive their signals. Once they receive the signal, then the voltage will be VAC. This voltage is VAC, and this is VAB, and so on and so forth. Now this only if we have a small firing angle and if we have a resistive load. Let's revise it again here. The voltage here is VB, but the voltage here is VC, right? And here VA and VB, and so on and so forth. So if you look at this point here, the voltage, the output voltage will be what? Will be VAB, right? This is VAB. But this VAB will not come to the output voltage, will not appear to the output voltage until VA and VA receive the signal. Now let's define the signal, the firing angle signals here. You'll find that here we have VA, thyristor 1 receive the signal here, and alpha is from here to here. Now VC, which is connected to thyristor 6 and thyristor 5, so in this case thyristor 6, okay, the bottom one, so this is thyristor 6. So thyristor 6 will take the signal, or will receive the signal at this point, and the firing angle is from here to here. Same thing here, from here to here, this is alpha, this is the firing angle, and VB, which is connected on the upper side with thyristor 3, so that thyristor 3 will receive the signal at this point. The same thing here. Here is alpha, and the bottom thyristor, which is connected to VA, which is Thyristor 2, will take the signal here, and so on and so forth. Okay, same thing. If you look at this one here, VC should conduct at this moment. So here VC, the upper side is connected to Thyristor 5, so Thyristor 5 will take over at this point, and finally VB, Thyristor 4, will take over at this point. Now these thyristors will work in this pattern. So Thyristor 1, okay, then Thyristor 6. Sorry, Thyristor 1, Thyristor 4 here. Okay, because this is conducting until this point. So Thyristor 1, Thyristor 4 will be conducting at this time period, okay, from here to here. And then Thyristor 6 will take over from Thyristor 4, then will be conducting at this point, and so on and so forth. Here, Thyristor 3 and Thyristor 6, 3 and 2, 5 and 2, and 5 and 4. And the only difference here, compared to the three-phase half-wave rectifier, you need to take into account both the upper side and the lower side of the waveform, the positive and the negative side. As if we have two half-wave rectifier, three-phase half-wave rectifier, the upper side is, the upper thyristors are concerning about the positive waveform, and the lower thyristors are concerned about the negative waveforms. Then finally, the output voltage will be something like this. It will be this voltage, and the output current will be same in shape with the output voltage, because the output is a resistive load. Okay, we have a resistive load. If we have an inductive load or high inductive load, you'll find that the output current will be constant, and then of course the behavior will be different. Okay, now let's go and try to find the average voltage for this waveform. What we will do here, I will take this portion, okay, and again I will shift it to be at 90 degrees, okay, and then I will consider it as a cosine wave. What we can say, it's V out of t is equal to how much? Cosine 2 pi t over t, okay, but this is multiplied by the root square of 3. Because the output voltage here is the line voltage. The input voltage is the phase voltage, but the output voltage is the line voltage, because it's VAB, the difference between the A and B, B and C, and so on and so forth. Okay, so here we'll make integration for the line voltage. This is very important. And if we make just for this portion, that's fine, no problems. So here, this is defined from minus t over 12 plus delta t, the firing angle period, until t over 12 plus delta t, right? So we can say V out, the average, is equal to how much? 1 over t over 6, which is 6 over t integral, minus t over 12 plus delta t until t over 12 plus delta t. For this cosine, which is the root square of 3 times v maximum, cosine 2 pi t over t dt. And you know now the integral for the cosine is what? Is sine. Okay, and we just substitute by these two values. You'll find that here we have at the output, and we divide by 2 pi. So here you'll get 3 times the root square of 3 times v maximum over pi times sine pi over 6 plus 2 pi delta t over t. Okay, this is the upper one here. Substitute here in the sign. Minus sine minus pi over 6 plus 2 pi delta t over t, and this is alpha. Now we know by definition that sine pi over 6 plus alpha minus sine minus pi over 6 plus alpha, this can be replaced by 2 sine pi over 6 times cosine alpha, right? Which is 2 pi delta t over t, and multiply this by 3, the root square of 3v maximum over pi. Sine pi over 6, which is sine 30, is how much? Is 1 over 2. Okay, just substitute this one here. You'll find that 3, the root square of 3, divide by 2 times 1 over 2, which is 1. okay, times cosine alpha. So finally, you'll get V out, the average, is equal to how much? 3 times the root square of 3 over pi times V maximum for 2 times sine 30 degrees is 1 over 2 times cosine 2 pi delta t over t. And here finally we obtain this one. This will be 1, and V out at the end is equal to how much? 3 times the root square of 3 times V maximum over pi times cosine alpha. And this is the average voltage for a 3-phase full wave rectifier, controlled full wave rectifier. Now what is the difference compared to the uncontrolled rectifier? For the uncontrolled rectifier, alpha was 0, so cosine 0 was 1, so the average voltage is like 3 times the root square of 3 times V maximum over pi, if you remember. So this is the average voltage without Thyristor. But the good point, we can change alpha. You can control with the average voltage, the amount of voltage that you get on the output, okay? That's why we call it controlled rectifiers. If you try to increase this alpha from 0 to 60 degrees, you'll get the same answer. After 60 degrees, the behavior will be changed. Now, if we have a 3-phase full wave rectifier, controlled rectifier, with R load, but a firing angle which is greater than pi over 3, what happens? You'll find that the output voltage will hit the 0 line before the next firing signal reach to the thyristor, to the coming thyristor, to the next thyristor, which means the output voltage will hit the 0 line, the voltage across the thyristor will be 0, then the thyristor will be off. We have resistive load, no current, no voltage in the output voltage will be 0. So again here, now this is alpha starts from here to here, so this is alpha, and we send signal to thyristor 1 at this point. So thyristor 1 received its signal here, and before this point we know that thyristor 4 is conducting, and here, so this thyristor 1 and thyristor 4 are conducting. But at this point, let's look at the next one here. Yeah, look at this one here. At this point, so this is alpha. You see, you can notice that alpha is very large, which is greater than 60 degrees. So at this point, thyristor 6 receive its signal. So here, this VA, this is VC. So the output voltage here, because thyristor 1 and thyristor 4 are conducting. So this is 1 and 4. So this is conducting here. 1 is conducting. Now look at this point. Here is the trick. Now this is VA and this is VB. But which thyristor is conducting? Thyristor 1 and thyristor 4. Thyristor 4 is conducting. Now VC is smaller than VB, but thyristor 6 here, which is connected to VC, didn't receive the signal yet. So the output voltage is VAB. Okay, so at this point, VAB. Why? Because thyristor 4 is conducting. At this time, thyristor 6 is not conducting, so VC, as if there is no VC there. So the output voltage, if there is diode instead of thyristor, should be VAC. But because we have a thyristor and thyristor 6 didn't receive the signal yet, so the output will keep conducting, it will be VAB. Okay? Until this point. At this point, what happens? VAB will hit the 0 line at this point, and the output voltage will be 0. Okay, because we have a resistive load. After this point, all switches, like no conduction. Okay, the output voltage is 0. At this point, thyristor 6 receives the signal, and then the output will be how much? VAC. Whereas we have VB. Yes, we have VB, but VB, the upper side of VB, thyristor 3 haven't received the signal yet until this point. So from here to here, the greater is VA, the smallest is VC, so the output will be VAC. So here we have VAC, the output voltage, as if it's shifted, right? You'll find VAC is here, but the output is shifted. Why? Because Thyristor receives the signal very late. Now, what we care about actually the output waveform here. The output waveform. We need to find the average for this portion from this point to this point. Okay, but we will take the average from here to here. So this will be 0, and we'll divide by this duration. So the integration from here to here, but the average will divide by this period. So let's say, for example, here we start at minus t over 12, and we will stop at t over 4. So this is minus t over 12 plus alpha or plus d delta t. Delta t, this is the very large alpha, right, which is greater than pi over 3. So the integration will be from minus t over 12 plus delta t until t over 4. But we will divide again by t over 6, okay, from here to here. So let's go and find the average voltage. So define the V out in time domain. Again, it's the root square of 3 times V maximum times cosine 2 pi t over t. And this is defined from minus t over 12 plus delta t. And if you want to make the average, it will be how much? 1 over t over 6, 6 over t, okay, from minus t over 12 plus delta t. Yeah, because here we have the output will be how much? How many? We have 6 portions, right? We have 6 portions, so we'll divide by t over 6 until t over 4 for the root square of 3 v maximum cosine 2 pi t over t dt. Again, cosine will be sine, so this will be sine pi over 2 minus sine pi over minus pi over 6 plus alpha, which is 2 pi delta t over t, and all this multiplied by 3 root square of 3 v maximum over pi. This will be 1, and you can simplify this. It will be how much? The output voltage is equal to how much? 3 times the root square of 3 v maximum over pi times 1 plus sine pi over 6 plus alpha, or pi over 6 minus alpha, because minus sine minus x, it will be plus sine x, right? So this will be plus sine pi over 6 minus alpha, right? So this will be minus alpha. And this is the average for the output voltage of a 3-phase full wave controlled rectifier with R load and a firing angle which is greater than 60 degrees. Now things are very simple with a resistive load, okay, because we know that the output current will be same as the output voltage in shape. So here, for example, you'll find that this is the output voltage, and the current will be just V output over R. You'll get the output current, and the output current will be same in shape with the output voltage. Now let's see if we have a 3-phase full wave controlled rectifier, but the output voltage, the output load is a heavily inductive load, a highly inductive load. If we have a highly inductive load and the firing angle that we use is a small firing angle, which is less than 60 degrees, you will not notice any difference, okay, compared to the resistive load. So the output current is constant, okay, no problems, and the signals here will be sent to the thyristors, like here thyristor 1, right, and thyristor 4 will be conducting, and so on and so forth. Here, for example, you'll find that this is alpha, and thyristor 6 will be conducting. So thyristor 6 will take over from thyristor 4 before VAB hits the 0 line. So you'll not notice any difference. The output current is constant, yes, but this will be exactly same the same case as the resistive load. Okay, you'll get the same average voltage, no problems. The average voltage will be same as the resistive load. The only difference here, we have the output current will be constant. The difference will appear only if we have a large firing angle which is greater than 60 degrees, like here. Look at here what happens. At this point here, we expect that VA, VB are conducting because thyristor 1, thyristor 4 are conducting. So the output voltage will be how much? It will be VAB. This output voltage will be VAB. But again, because thyristor 6 receives the signal at this point, so VC will take over only after this point. But before this point, VC as if it's like disappeared. Why? Because thyristor 6, which is connected to VC, the lower side, is not conducting. So the output voltage here, VAB. This is the same case as the resistive load until this point. Okay, so here we have VAB, no problems. Now at this point, VAB hits the zero line, okay? But because the output load is a highly inductive load, so thyristors will keep conducting. So this will keep giving VAB at the output, even though this is a negative voltage. So this will keep conducting until thyristor 6 here receives its signal. Then the thyristors which are conducting will be thyristor 1 and thyristor 6, and then the output voltage will be directly VAC. This is a VAC voltage. Here we have the same thing. Okay, at this point we'll keep conducting until thyristor 3 take over from thyristor 1. So all this time thyristor 1 is conducting. So from here to here, thyristor 1 is conducting. At this point, thyristor 3 will conduct. Then the output voltage will be how much? VBC. This is B, VB, and this is VC will keep conducting. So the output will be VBC. Like if you look at this here, for example, thyristor 3 and thyristor 6 are conducting. So we have to take into account VB and VC. We don't need to look at VA, right? Because now VA connected thyristor 1 on the upper side and thyristor 2 on the lower side. But at this point, neither thyristor 1 nor thyristor 2 is conducting. So VA as if we have no voltage VA, okay? So the output will be VBC. So you need to look at which thyristor is conducting first, okay, then find the output voltage, which is different than normal rectifiers. Normal rectifiers, just you need to look at the output voltage, the upper and the lower, the greater voltage and the smallest voltage, okay, and you'll see that the greater VA, the smallest VB, then VAB, easy, okay. But here no, you need to look at which thyristor is conducting at this point. If the thyristors which are conducting to the phase don't have any signal, then as if they are invisible, okay, and then the output voltage will be here, for example, VBC. Look at here, for example, same thing. Thyristor 3 and thyristor 2 is conducting. Thyristor 3 means VB, the upper side, and thyristor 2, which is VA, the lower side. So the output will be how much? VBA, right? Will be VBA. This one, VC, invisible. Why? Because the thyristors which are conducting, which are connecting to the VC phase are not conducting. They don't have any signal at this point. Okay, so here we have VBA. Okay, so the output will be VBA from here to here. Okay, again, here this is negative, but this will keep conducting because what? Because the output current is constant, because we have inductive load. Okay, so we have current on the output, so the current will drive at this point. We'll keep conducting these thyristors. Look at this one here. The output is VCA. Thyristors 5 and 2 are conducting. 5, which is thyristor VC. So VC only will conduct at this point. Conduct at this point, VC, and VA will keep conducting. So the output voltage here is how much? VCA. Look at here, VA became greater than VC, okay, but this will keep conducting again because what? Because the output current, because we have current on the output, and this current inductive load hold the current, no way to leave any thyristors to be off automatically. There must be another thyristor to take over, which is at this point thyristor 4 will take over at this point, and the output will be how much? VCB. VC will continue, okay, and VB will conduct at this point, and then the output will be how much? VCB. This is the output voltage. The only difference here is that at zero line, again, you'll find that thyristor will keep conducting and the output voltage will be negative because of the output current.